Now, in this video, we're going to look at solving systems of linear ordinary differential equations. And we're going to talk very, very briefly about sort of the theory behind this. If you want sort of a more formal derivation, you definitely are going to need linear algebra for this. But just to conceptualize this, if we're talking about solving an ordinary differential equation in one variable, with this setup where we just have a constant times the function equal to its derivative, then in the one variable case, we would use separation of variables, and the form of the solution that we would get would be y is equal to our solution function is equal to some constant times an exponential function. Now, this is actually going to be somewhat generalizable to the multivariable case where we have more than one equation, but we're going to make replacing some of these constants, they're going to be converted into the form of matrices. Now, the exact process for how we do this is somewhat more complicated. And so one of the sort of foundations has to do with how do we actually raise e to a matrix power. And generally, we do this using Taylor series. So e to the x can be expressed as this Taylor series, as this power series. And so we can raise matrices to powers. And so we can actually use this definition to come up with an expression where we can raise e to the matrix power and then use the Taylor series to figure out what this looks like. Now, for generic matrices, this is quite complicated to calculate. But if we have a diagonal matrix, and many, many, many matrices can be diagonalized, in the case of a diagonal matrix, this ends up just being A, if A is just has values on the diagonal, then when we raise A to the power of n, then the diagonal just gets raised to the power of n. And so we can then think of this as each of these terms in the first component and the fourth component of our matrix are just going to be themselves, each one raised to that same power, which gives us exponentials in each of these entries. And so we get e to the first element and e to that fourth element, and the off diagonal is 0. Again, from linear algebra, you can diagonalize almost any matrix, and therefore we can apply that same property to any matrix A. If you raise it e to the a power, you can calculate the diagonal version of that matrix and then do the transformation to make it back to the original matrix. This is the linear algebra piece. So we're not going to worry too much about that. We don't have to prove that as we go through the system, but there is math behind it. And so if you've taken linear algebra, or if you're in linear algebra right now working with these systems, then this process of understanding that relationship between e to the a is going to be familiar to you. And then our constants a will be a not a matrix, but they can be a vector in order to get our vector solution. We are going to primarily, for a differential equations context, we are going to basically use enough linear algebra to execute the solution and not worry about the theoretical side of it. But certainly, if you're in a linear algebra class, your typical textbook will walk you through sort of the entire process of how to justify this, what we're doing. So let's actually go solve our worked example for our two variable case, two equation case. So we have this set of linear ODEs in two variables. The derivative of x1 with respect to t depends on both x1 and x2, and the derivative of x2 with respect to t depends also on both x1 and x2. if we write our vector x as x1, x2, then we can say this is the derivative with respect to t of this vector, and these coefficients can come out as a matrix. That's our A matrix, and being multiplied by the original x1, x2. So we have a equation that is of the form of our one variable case. The derivative of our variable is equal to some constant times our original variable. That is the connection between that first order case with one variable and our system. And what we know from the sort of introduction that we briefly discussed is that our solution is related to the eigenvalues of our A matrix, because that's how you diagonalize at an A matrix generally. And so we're going to need e to the lambda at lambda 1 and e to the lambda 2, assuming we can find two eigenvectors, two eigenvalues and two eigenvectors. And then we're going to write our final equation of this form, where v1 and v2 are going to be the eigenvectors, lambda 1 and lambda 2 are the corresponding eigenvalues, and then c1 and c2 are our coefficients that provide us that any linear combination that we need in order to get to whatever our initial conditions are. So we're going to obtain our solution by finding the eigenvalues and then the eigenvectors. So we're going to take our A matrix, we're going to subtract minus lambda I, which is minus lambda on the diagonals, find our determinant. So this guy times this guy minus this product. And so we get this. It's our characteristic equation. We FOIL everything out. We get this polynomial. And then this factors as lambda minus 2 and lambda plus 1. And so our two eigenvalues are 2 and negative 1. From there, we have to find our eigenvectors. So we're going to plug lambda 1 into our A minus lambda I matrix right here. And so if you have 3 minus 2, you get 1, and negative 2 minus 2, you get negative 4. What must happen for this to work is that your equations are now multiples of each other. If they are not, you have made an algebra mistake someplace before you got to this point. In this case, the top equation times 2 is the bottom equation, so it is dependent. And so we can find the required eigenvector. We would pull out one of our equations. In this case, I pulled out the top equation, and I set the second variable equal to itself. It's a free variable. And then solve your left side of the equation for x1 in the first equation, and you get this x1 is a multiple of x2, and the coefficient vector here of x2 is, in this case, 2, 1. That is your eigenvector. Again, if you're unfamiliar with solving for eigenvectors, then you should probably watch more videos on solving those. This is assuming that you basically understand the process. Then for lambda 2, again, we plug in negative 1, 3 minus and negative 1 is 4. And then in the bottom one, negative 2 minus and negative 1 is going to give me negative 1. This equation times 2 is the top equation. So I'm going to take the bottom equation because the coefficients are smaller. And I'm going to, again, solve the top equation for x1 and set the bottom equation equal to itself. And now if I plug x2 equal to 2, I get x1 is 1. Again, it's very helpful to kind of not use fractions in your vectors. Choose your value of x2 so that you can get nice whole numbers. And then when we put everything together, our 2, 1 vector went with lambda equal 2. So this becomes C1, our vector 2, 1, e to the 2t. And then in the second case, our 1, 2 vector, and our lambda was minus 1. Now we can split this up into two separate equations. x1 is equal to 2c1 e to the 2t, and also 1c2 e to the negative t. And in the bottom equation, x2 is 1c1 e to the 2t, and then 2c2 e to the negative t. And from this, we can actually start thinking about how to plot these vectors, these solutions, as parametric equations. Now, the eigenvectors themselves can be plotted in terms of a slope. So you can think of our vector AB as the change in x over the change in y per time. And so your slope of your line for that goes through this vector is going to be delta y, which is the b, over delta x, which is the a. In parametric form, these would be x is at and y is bt. And so we can graph the eigenvectors along with our solution because we can expect that the behavior of the graphs will tend toward the eigenvectors, particularly in this case where they're in opposite signs. So I'm going to plot my two graphs. Now, I left C1 and C2 to be specific A's and B's, and I set the values into that on a separate set of equations. On a different screen, I set A equal to this and B equal to that so that I could change the values, or I could change the values without having to rewrite my whole equation. But if you plot your x1 and your y1 from the differential equation, and then here I'm plotting my eigenvalues and eigenvectors, the lines that correspond to those. In this example, if I choose a particular A and B value with some initial starting position, such as this, you can actually see as time changes, the path of the system. If you change them again, you try and choose a different set of initial conditions, you can see that in this portion of the graph, they would behave like this. And then similarly, you could plot initial conditions that were up here or over here, and you would see that characteristic behavior of the origin behaving like a saddle point. It's neither attracting nor repelling. Now, in the complex case, things are a little bit more complicated, and so we're going to save that for part 2.